All right, are you about ready?
Yes.
Wonderful. I will let them in.
Okay. Well, greetings, everybody. I think we have most people present for lecture three. And let's just take stock of where we are over the first two lectures. I introduced a bunch of the terminology that's pertinent to quantum mechanics and terminology and concepts. And we're now ready to dive a little deeper and get a view of how quantum mechanics works. I'm going to show you lots of examples of the kinds of problems that we can solve. And so let's get started. First, of course, we have to have a little cartoon. This is Schrodinger's cat, wanted dead and alive. And little humor goes a long way when we're dealing with these complicated topics. Let me clean up the screen just a touch here. Okay, so let's do a summary of what we've talked about. And these are the key points that are listed here. Today, we're going to see a lot of emphasis on the wave function, which is a mathematical entity used to describe quantum systems. And the use of the wave function has not changed in 100 years. The invention of the wave function by Schrodinger in 1926 has stood the test of time. And I've said this before, but it's worth emphasizing, all the electronic technology that we have in the modern world comes from manipulating the wave function, understanding how to design semiconductor devices, lasers, and other technology that we enjoy. There still remains an issue about how to deal with the wave function. That is Schrodinger's equation, and we're going to take a look at it, just treat it as like a piece of art. But
Hey, Ed,
yes,
would we be able to make the screen better or bigger? We got some people in the chat asking if we can make it bigger.
uh, let's see, I'm sharing the document we're looking at. I don't think this is going to help, but you let me know if that helped. Wait, does that help?
I don't think so. I think they're wanting to make it single page if possible.
Oh, okay, we can do that. Uh, so it's more like this.
Yes, that looks bigger to me. I'll let
Okay,
you know if anyone else says anything.
all right. All right. So we talked about wave functions. Now, there's still an issue with quantum. How do we interpret what quantum mechanics tells us? Because there are two intervals that apply in the quantum world. One is the interval described by the Schrodinger equation, and it tells us how the wave function changes with time and space. And from that, we get the probability of certain outcomes from measurements we might want to make. But as soon as we make a measurement, we enter a brand new interval described here in which the wave function disappears and we just have a single value for the result. And there's in the what we call classical physics, we never see this kind of partition of the evolution of classical systems. The progression with time is predictable. You know, if you watch somebody hitting a baseball, there's no transition from one description to another. Quantum mechanics, nonetheless, has this unique feature, and it's constantly being debated. What does that mean? And we will talk more about that. Uh, the other thing that's pertinent about the wave function is the square of the wave function tells us the probability of the outcome of some kind of experiment or natural process. And again, we're going to see wave functions uh, later on today. Okay, let's see. There's some other, oh, okay. And we've talked about this before that quantum systems can exhibit particle-like or wave-like behavior depending on the environment you present to them. And we have this example of the double slit experiment where we can, these lines represent a flow of light that finds its way to a slit that collimates the light, and then there are two slits here. And just like with sound waves and water waves, we see interference. That is, we see areas where it's not much energy, and then there's energy sort of depicted this way. So this is a double slit experiment, and we now know and have for a long time been able to demonstrate this kind of interference pattern using quantum particles, photons, electrons, the subatomic particles like neutrons and protons and so forth. So we can see with an experiment of this type the wave-like behavior of the quantum world. We also see particle-like behavior if we do different types of experiments. So, and here's an example of really interesting behavior. Let's click on this. Oh, let me do something. I'm going to stop sharing, and I'm going to share my whole screen because I want you to see this. The because I'm now in, I'm showing you something from the internet. You're seeing this, right? That there are dots appearing on the screen here.
Yes, we can see it.
Okay, so what we're looking at here is a very uh, interesting example of the wave particle behavior of quantum mechanics. So this is actual experimental data. And I'm going to let this keep running. It repeats itself, and I'll explain along the way. What we're seeing here is a situation where electrons are exposed to a double slit experiment, not light, but electrons. And normally we think of electrons as little BBs or something. But this shows us the emergence of a diffraction pattern, or interference, sorry. And what I'm going to do, I'll put these side by side like this. Here's an example of the double slit using light. And you see these bands of bright and dark regions. This only happens if you're dealing with waves that can interfere with each other. If you look at this, you'll see the same kind of behavior emerge. Over a period of time, electrons passing through a system equivalent to this, produce bands of bright and dark. So there's compelling evidence, and this is not the only way to show it. There's compelling evidence of the wave-like behavior of physical particles, in this case, electrons. You can also see this, as I said, with all the subatomic particles and so forth. So let's stop that, and we'll get back to, so we're summarizing the properties of quantum mechanics that we've discussed in prior lectures before we actually start working with it. There's a snapshot of that experiment showing particle-like behavior by electrons. Here's a depiction of that issue I mentioned earlier. Here's time. And in green, we have the wave function of some imagined experiment. And the wave function changes with time. And then right at this point in time, we conduct an experiment. We measure something or we observe a natural phenomenon. And instead of having a wave function that predicts this range of possible outcomes, this is in blue, psi squared, instead of having that persist and be part of the prediction process, we get an experimental result. And we, for example, this could be where one of those electrons landed on the detector system that I just showed you. So we have a wave function defined by the environment in which the quantum particle exists. The wave function tells us the probability or the prediction for outcomes of experiments or measurements, and then we get a result. And then if you let that the particle go to another experiment, the same thing repeats itself. But right here, this transition is an unexplained part of the process, because on the left side, the earlier time, we have a descriptive process, the Schrodinger equation and the wave function. On the right-hand side, we have a result. And one of the features of this is if you're given a result of a quantum experiment, you can't go backwards and talk about where'd that result come from. It's not a reversible process. If you take a film of a billiard table and watch a player hit one ball into the other, and you see the trajectories of the balls, if you run that film backwards, you'll see the balls come together, strike each other, and go back to their starting points. But it's a reversible process. That is, in the classical world, with some exceptions, things are reversible. This process is not reversible, and that remains a kind of a mysterious part of quantum mechanics. So let's take a look. This is the Schrodinger equation. I know there's a lot of crazy symbols here. Most of them can be ignored, except the key things. The wave function, psi, is a function of position, x, and time, t. And then there's some mathematical apparatus here. But here we see some of the interesting features. First, we have I, the square root of -1. This is Planck's constant. This is the mass of the particle. There's Planck's constant again. And so when you see these kinds of equations, and we'll see another version of this later, just notice we're counting on Planck's constant and the mass of the object when we do this calculation. And the result, this is Schrodinger's equation, the result is if I put into the mathematics the conditions in which this quantum system exists, I will get the wave function. And the wave function squared tells me the probability of the outcome of a measurement or natural process. One of the very interesting things that happens when you do these kinds of calculations is captured in this quote. Integer numbers, the numbers 0, 1, 2, 3, and so forth, come out of this in every case. The solutions to this do not allow energy levels of hydrogen, like I discussed last week. You don't get solutions that depend on something different than integers. That's an intriguing feature of this, and it's related to the name of this whole science. It's quanta that are typical results of manipulating the Schrodinger equation and the wave function. Now, we can simplify this if we're looking for something that doesn't depend on time, and a whole bunch of stuff goes away, and we get this simple form where we have the Planck constant, the mass of the quantum particle, and the energy of the system that the quantum is in. So keep this in mind because we're going to do some examples. And here are, but before we do, we're going to talk about the properties of wave functions. Remember, the wave function is a mathematical entity, and it has to obey certain rules so that it comports with the mathematics that's going to be applied to it. And the key thing is the time evolution of the wave function psi is defined by the environment. And I'm going to show you some environments in a second. But what's critical is it can't do these kinds of things. From a mathematical point of view, a wave function doing something like this is unacceptable. This sharp point here is not compatible with the properties of the Schrodinger equation. It can't do this either. If this is time or space, it can't have a value that's different, two different values at the same place, for example. That creates a problem. It can't have a gap like this. It has to be a continuous, what we call a continuous function. And here's another example of it cannot do this, where you have a whole bunch of locations or times where the wave function has different values. That confounds the ability to actually do the business of solving the wave function. And so what we need is, and in addition, in virtually every case, we need the wave function to dissipate down to zero when you're far away from the location of whatever experiment or observation you're going to make. So far, far away, the wave function exists, but it has essentially a zero value. Here's a footnote about that square root of -1, which created a lot of confusion in the early days of quantum mechanics, because if I write down a wave function that has this in it, then it can't be part of the real world. In our world, we have mathematical description of what's going on, but we never use imaginary numbers except to get to the answer. The world itself cannot be imaginary. So let's take a look at some examples. These are I'm going to show you a couple of animations. Here's one for what's called the quantum harmonic oscillator. Basically, it's this object here connected to a spring, and it just bounces back and forth. So let's take a look at this, and you can see what's going on here. As a function of time, as the object, well, first of all, what we're doing is look at this as a classical harmonic oscillator. A good example of a harmonic oscillator is a pendulum. It's something that goes back and forth, and if there's no friction or air resistance, it'll just persist forever. This is what the quantum version does. These are the wave functions, and they're in different colors because part is the real value and the other part's the imaginary value, but we don't have to get tangled up in that. Notice that as the object oscillates back and forth, the shape and amplitude of these wave functions is varying. The wave function also dissipates in time. This is one of the another unique feature of quantum mechanics. If you have a quantum particle and you analyze it with the Schrodinger equation and just let it sit there by itself and don't have it interact with anything, it just fades away. So what this is showing, it's a little hard to see it, but initially there's all the energy and the wave function is concentrated right there, right in the center of this, but then it kind of spreads out. So we have these natural properties of wave functions. Again, here's the Schrodinger equation. So keep those in mind. These are in the book. You just click on this and you can see that animation again. And of course, there's a discussion here of trying to explain this. Now, what's important is in a second, we're going to look at what the cloud of probability for electrons in atoms looks like. And there are multiple integer numbers that describe the shape and other properties of that cloud. And they have to do with the energy, which is traditionally dictated by the integers designated by n. There's angular momentum, and there's spin. So to fully describe the behavior of a hydrogen atom, for example, we need to know these numbers as they pertain to what the electron is doing. And here's what you get from that. Let me make this a little bigger so it's easier to see. These are the three-dimensional depictions from the mathematics for different energy levels. That's n equal 3, and orbital, and the orbital angular momentum number is 1. The spin number is, in this case, -1. So we get these really interesting three-dimensional shapes that tell us if we could track a whole bunch of hydrogen atoms and take snapshots to see where the electron is. Now that's a loaded statement I'll get back to in a second. Where the electron is, that we would get probabilities. Every one of those snapshots we take, you'd see the electron in a different place. Of course, the electron is not a particle. It is spread out. It's around the nucleus, and its probability of being in any one place is depicted by these predictions. These are the values of the square of the wave function. And if you slice through these, you can see the cross section here. Here's the ground state of hydrogen. And here are more complex states. If you look for this one, 3, 1, -1, there it's here. Those are fours. It's like this one. In fact, there's a 3, 1, 1, and I think there's a 3, 1, 1 here. Yeah, this and this depict in 3 dimensions and in 2 dimensions the distribution of the electron in hydrogen. And this is of interest to chemists because they want to know how the energy levels of atoms redistribute how the electron is behaving so that they can predict the behavior of compounds where the electron clouds of different atoms are interacting to form solids, gases, liquids that have molecular structure. And we'll see more of this in a few minutes. So this comes from solving the Schrodinger equation for the hydrogen atom. This supersedes what Niels Bohr did in 1913 when he used his planetary model to predict the energy levels of hydrogen. And his version of the behavior of electrons in hydrogen gives you exactly the right answers. But the strategy of treating the hydrogen atom as like a moon orbiting Jupiter, where Jupiter is the nucleus of the atom, that we don't do that anymore. It's taught as a historical step in the progression of quantum mechanics, but this is the right way to do it, and it involves some sophisticated mathematics to get these shapes. So we'll look at another animation. So here we have the ground state of hydrogen, that's called 1s. And with this mathematical tool, this is a physics-based tool, you can decide to well, first of all, you can see the distribution of the electron cloud, the probability cloud is spherical. But suppose we're interested in another more complex energetic system, like with an energy level of 3. When you click on that, it takes a few seconds for the math to do its thing, and we get this. With this tool, all I'm doing is putting my cursor on there and dragging so you can see three-dimensionally. These are the places where the electron is most likely to be found. Notice right in here, the electron is never there or there. Let's try one more of these things. Let's do a energy level 4. Once again, we have to wait for the arithmetic to occur. So you see these beautiful shapes. The interesting thing is all the mathematics that represent solutions to the Schrodinger equation for the atomic orbitals of the elements. All that mathematics had been discovered in the 1800s as an intellectual exercise. The chance that the mathematicians that made those developments had no reason to believe that their work would ever be useful. And yet, here it is. These are the solutions for hydrogen in this case. Now let's talk about a major step forward, and that is the Born rule. Here's Max Born. He was an expert at solving problems with the Schrodinger equation, and eventually realized that the outcomes of the experiments he was considering were depicted by squaring the wave function. So he solved the wave function, solve the Schrodinger equation, get the wave function for the system under consideration, and then square it. And when I say square it, there's a little wrinkle to how you do that, but basically it is the square of the wave function, and that gives you the probability of finding the result. These are the squares of the wave functions for the various energy levels of hydrogen. This is his granddaughter, Olivia Newton-John. And there's a discussion here about how he produced his result and the criticism of it initially. Eventually, people realized that what he had done made sense. And in fact, this is Einstein writing to Schrodinger, talking about what do we do with the wave function if we don't adopt the Born rule. And the Born rule, I should have highlighted this. This is something I wrote. I'll deal with that some other time. The new copy that you'll have will have that highlighted. So there was criticism, and this is the way science works. Somebody came up with an innovation, and people looked at it, and it's rare for a development to be accepted by the community immediately. So in any case, Born had enormous impact. Also, about this time, this was in the late 20s, early 30s, we start seeing a new generation of contributors. In the prior two lectures, I've talked a lot about Einstein and Max Planck and so forth. They were trained in the 19th century in the classical physics that preceded quantum mechanics. By 1925, everybody was a young buck. You see some of the ages here. In fact, Dirac was the first one to earn a PhD in quantum mechanics. The exceptions, the ones who stayed with the science and kept making contributions, but from the first generation of quantum mechanics, were Schrodinger and Max Born, both of whom won the Nobel Prize. Speaking of the old guard, this is a picture of the grave of Boltzmann, who was a giant in the field of thermodynamics in the 19th century. And on his tomb, there's an equation that relates to his work. In fact, many of the scientists have relevant equations on their graves. Um, I have pictures throughout the book. There are pictures of their gravestones. So another property of that I've alluded to at the beginning of this lecture relates to the wave-particle duality. So I built this table that talks about how to understand the wave and or particle behavior of light. So this is sort of a historical view. And the key thing, sorry, I had to deal with a phone call. The key one is this. Louis de Broglie, working on his PhD thesis, was following the developments. This is between 1920 and 1922. He was following the developments related to characterizing the properties of light, particularly this issue here, where Einstein struggled alone for a number of years, close to 20 years, to convince the community that light could be described as particles or waves. And I've talked about this before. I'll remind you that Newton, 300 years earlier, had proposed that light travels as little packets of light he called corpuscles. John Young's experiment in the early 1800s, 1808, showing the behavior of light passing through a double slit, showed wave-like behavior. And then there was a long period, essentially 100 years of confusion about how is it that light sometimes behaves like particles, sometimes like waves. Einstein, through his work and his philosophy, and demonstrated repeatedly that light could behave in either way. And de Broglie picked up on this and said, if light can be a particle or behave like a particle or a wave, then maybe particles like electrons, neutrons, and so forth, maybe they can behave like waves. And so this was a major step forward. Eventually, de Broglie won the Nobel Prize for his advance. And a number of experiments proved that he was right. In the modern version of those experiments that we will see in lectures, mostly in lecture 5, we talk about how to exploit this wave-particle duality to get more insight into what's really going on. One of the key applications of exploiting wave-particle duality is that we can build microscopes with particles. So here's a picture of some kind of biological entity, here it is. It's a plankton, floats around in the ocean. It's a plant, but it's in the ocean, counting on sunlight to produce energy and so forth. So this is about the best you can do, getting the detail of this plankton using a microscope where you shine light on the object and then have an optical system, namely a microscope. The wavelengths that are used here are in the visible wavelength spectrum. So between 400 and 700 nanometers, that's the sensitive range of the human eye. But if we do the same experiment with the electron microscope, here's this, where these are on the same scale. Look at the level of detail we can get, because an electron behaves as a wave with extremely short wavelength. And here's the example. The resolution from a optical system is about 200 nanometers. And that's from using green light. Here's the wavelength of green light. But if we use an electron microscope and apply the rules of quantum mechanics, suddenly we go from resolving 200 nanometers down to zero point 0.1 nanometers. So that's an improvement by a factor of 2,000 in our ability to see details. It's an extremely powerful technique. So let's take a look at solutions to the Schrodinger equation. Remember, the Schrodinger equation by itself is just an abstract approach to manipulating the wave function, or solving for the wave function. But we need to know the environment in which we are working. And the first one that physics students learn is this one. We place a quantum particle in what is called an infinite potential well. There's some parallel here between, let's say, a water well, a deep water well, and how hard you have to jump to get out. How much energy does it take to jump from the floor of the well out and escape? Particular case that the first thing that students learn is when this is infinitely deep. So no amount of energy can get you out. So the particle is trapped in here and there's no way to get out. So we can put these restrictions shown graphically here, we can put these into the Schrodinger equation and find out what is the particle doing down here? How does it relate to the energy levels that it might have trapped in this infinite well? And here's what you get. Again, we don't worry about all the detail here, but I want to emphasize there's Planck's constant. There's, of course, the number 8. The mass of the particle, A is the width. Here, I have it as L here, but it's A here. Something for me to fix. So this is all the detail of the energy, but it depends on the integers, 1, 2, 3, 4, and so forth, squared. So again, we see evidence of quantization in the behavior of a quantum particle trapped in an infinite well. It will have energy levels. You can add energy to the particle, and those energy levels have to behave according to this. There can be no case where the energy level has, for n, some number other than these integers. They must have integer values. So that's a form of quantization, and you can extend this is a one-dimensional case. You can also extend this to a two-dimensional case, and what we find is the particle, where you might find that electron or neutron that you put in there, it's most likely at one of these peaks. If you manage to look in there and find out where am I seeing the electron, its peaks are distributed like this. These bumps tell you where you're most likely. Notice there's the wave function. You square it to find the distribution in space, and this is the result for an energy level where you put a 4 in there, and then you square it. Everything else stays the same. So what I'm going to do here, while I'm still thinking about it, indulge me for a second. I'm going to highlight this in red because I know I got to make some edits there that you will see in the updated version of this chapter in the book. You all realize, I hope, that you are guinea pigs. This is the first time I've taught from the book I wrote for this course, so you'll see little changes every once in a while. You can always check here. This is the date of printing of this chapter, and make sure the version you have is the latest version. Okay, so what we've seen is a number of things here. quantization in the energy levels of a particle trapped in an infinite well. Now let's change the conditions and let's let this well be not infinitely deep, but it has some finite depth. So you put the particle in there and see what happens. Now we get different solutions from the applying the Schrodinger equation to get the wave function for this situation. And the difference is right here in green. Notice the wave function now penetrates into the wall, which means that the particle might be found in the wall. Indeed, if we make this wall thin, there's a non-zero probability that the particle that we put in there will find its way outside of this well because the well is not infinitely deep. And again, the difference in this calculation and this calculation is how you add these properties of the circumstance of the quantum to the Schrodinger equation. So here we have the wave function penetrating into the wall. And it turns out this has an application. There are tremendously successful application is the tunneling microscope. We're going to see an example of that in a few minutes. There are electronic devices that rely on tunneling of this type. And the first application of understanding this process occurred in the 1920s when people were thinking about why radioactive elements are stable, they sit there, and then suddenly something pops out and the nucleus changes. And it turns out it's a tunneling process in some cases. This was worked out in the mid 1920s. George Gamow, who has his name assigned to the main physics building at the University of Colorado. It's called the Gamow Tower. He was a prolific scientist, but one of his early successes was to apply the properties of tunneling in the nuclear application of quantum mechanics. You might also have a system like this, where there's a particle in a system with walls that can be penetrated, and the particle can move around. It can tunnel through. So if you look at this system and look to find the object, it might be here, it might be here, it could be anywhere in there. Here's the wave function you get for this particular situation. It's a little hard to see here. This is a two-dimensional depiction of a harmonic oscillator. I already talked about a harmonic oscillator is something like a pendulum. If you put an electron in a bowl-shaped system like this, it will take on certain energy levels. And this one's very interesting. Here are the energy levels. We don't have to worry about that. Just look at this part. N plus a half, where N can have any integer value. That means that the harmonic oscillator always has this little bit here. It never has zero energy. So the lowest energy level, it's stated right here, the ground state, which is the lowest energy level of a quantum particle in a harmonic oscillator, does not have zero energy. It's sitting down there rattling around. And Sidney Coleman said this, that theoretical physicists just get more and more abstract versions of quantum oscillators. And here's an example. I don't have a picture for about what I'm about to say, but imagine a crystal like salt. It has sodium and chlorine atoms bound together by electrons that they share. And all those, the nuclei of the sodium and the chlorine are are always moving around because the temperature of the salt gives them energy. So they're always oscillating around. And that's a quantum oscillator problem to figure out how that system behaves with respect to temperature and other conditions. Here's a quantum solution for something where you drop a quantum object in the gravitational field of Earth, for example. Where are you likely to find it? And the answer is not on the floor. This is the floor down here, and this is higher altitude here, because it has, when you solve the Schrodinger equation, the most likely place to find it is at this altitude. And there's a little description here of that sort of condition. Now let's compare, using the Schrodinger equation, let's compare the probability of where the electron is in hydrogen, that's red, and helium, which is the dotted blue line. And you see an interesting thing, that the red position, the most likely position for the electron, is farther away from the nucleus. This point 0, that's the nucleus of the atom. In the hydrogen case, there's only one proton in the nucleus. So the electron is less bound than in the case of helium, which has two charged particles in its nucleus. And so it's much more likely for the electrons in the cloud around the helium nucleus to be closer to the nucleus. And so you see this depiction here. And it turns out also the Heisenberg uncertainty principle plays a role here. So here's a little anecdote about Gamow and his work in nuclear tunneling. And in fact, if you click on that little link, you get to a little demonstration you can do. This is from the University of Colorado. And if you choose to study polonium, a radioactive element, here is the nucleus. Now we're talking about applying quantum mechanics to the nucleus, not to the electrons. And you see this is the potential well, kind of like the first examples I showed. And I don't know if you noticed, just then, the polonium threw out a particle and became lead. See, it's not PO anymore, it's PB. So let's start this over. Where's the reset button? Oh, here it is. Yeah. So we have polonium 211. That tells us the behavior of the nucleus. And suddenly a particle gets thrown out because of tunneling. And now we have lead 207. And the half-life turned out, here's the half-life. It's not the same for every atom, but on average, the half-life of that kind of decay, because of tunneling, is 0.6 of a second, 645 milliseconds. So this is the kind of thing that Gamow was able to do once he understood that tunneling was a feature. I mentioned we have scanning tunneling microscopes that rely on tunneling. This is a depiction of a quantum particle, let's say an electron, captured in a energy well that can be penetrated. And we see it right here. The wave function has leaked out. And what we're seeing here is a little depiction of how this works. They have a tungsten tip that goes over a surface following the shape of the surface. And here's an application. This is called a carbon nanotube. Sorry about the spinning wheel. It's Microsoft Word updating this document. This is a carbon nanotube. This is a kind of a relatively recent invention. People know how to make these carbon tubes. And look at the dimensions of this. It's 7 nanometers long. That's this distance, and 1.4 nanometers in diameter. And these black or dark dots are individual atoms, carbon atoms that are imaged by the scanning tunneling microscope, relying on this tunneling feature that quantum mechanics gives us. I mentioned, actually showed, that the wave function spreads with time. And it's related to the uncertainty principle. If you try to confine the wave function, it will spread out. And here's some examples of what happens. For a low mass particle, it starts with this wave function. And this sort of arbitrary time scale. Notice how it gets fatter and fatter. And in fact, when that happens, the peak goes down. So you have this evolution. A larger, more massive object, starting with the same wave function, expands less slowly. See that here. And this all comes from the Schrodinger equation, and this is observed in the mathematics and in experiments. Let's see, this, we're going to go to reference 63. So here's a depiction of, well, let me make this bigger. This is a depiction of the spreading of a wave function with time. Let me get this. So it starts out fairly compact, and then it just kind of blurs out. You see over here, it's small and then larger over here. So we have this spreading of an uninterrupted atomic or quantum system. And I'll let you all digest this cartoon at your leisure. Whenever we're doing or talking about these kinds of things, we have to take into account the uncertainty principle, which says that we can measure properties of a quantum object, but not without limit. Let me get that out of the way. And this has an interesting parallel to another branch of physics. So the way equationally, the way this is depicted is this, that the measurement uncertainty of the momentum of a quantum particle, which is related to its speed, and the measurement property of its position, when you multiply those two uncertainties together, it has to be bigger than this number, where, again, that is Planck's constant. And the parallel this has is to optics. In the early 19th century, the competition between particle and wave descriptions of light revolved around the use of mathematics that predicted that wave-like properties of light could be tested by studying how lenses focus. And indeed, so I have this cartoon here of light coming to a lens, and what the scientists of that era discovered was mathematics says that no matter how perfect you make this lens, it will not focus to an infinitesimally small point. In fact, to shine light on a lens and focus it as well as you can and treat the lens as if it's perfect, You don't get a little spot where all the energy is located. You get this very interesting and beautiful shape. You get a peak surrounded by rings of that get smaller and smaller as you go away from the center peak. So this is called diffraction. And all the scientists who were at the foundation of quantum mechanics knew about this because it was this mathematical description of how wave-like light interacts with lenses. They all knew that physics. And Heisenberg was the first to realize that because we're describing quantum systems with waves, just like we can describe optical systems with wave-like light, that we should see an effect like this where we can't get perfect description of the properties of a quantum system. And indeed, his result was this, where the uncertainty in momentum times the uncertainty in position is always, that should be a larger than. So again, I have to make a little quick edit. Okay. This product of uncertainties has to be larger than Planck's constant divided by 4 pi. And you see it here. Here's the position measurement we would like to make. And we make that measurement. We say the best measurement we can make is that value. But we have some uncertainty. Like any other measurement, there are error bars. You probably encountered this in a chemistry lab or any other place you make a measurement. At the same time, we would also like to know the momentum. And there's the best estimate we have, but that also has an uncertainty. And the product of those must be bigger than this. And there's a physical interpretation that compares with the behavior of light. And it has to do with a thought experiment that Heisenberg created, which is think about trying to locate a quantum particle, say an electron. How do we see things? We shine light on it, and then the reflected light comes to our eyes or scientific instrument, and from that we can make an estimate of the location. But if we want to localize an electron, we have to hit it with high energy light so that we can resolve its location. And the process of shining the light on the electron actually influences the electron. It accelerates the electron. We never see this in the modern, in the macroscopic world. If you want to see an automobile, the sun provides enough energy so we can see the position of the car without the sunlight moving the car. But in the quantum world, that's not the case. And so, in fact, Heisenberg invented what is now called Heisenberg's microscope. I'll show you a picture of it. But the upshot is, if we localize, this is a depiction of a wave function. If we localize the wave function so that we know that the object is somewhere in there, the momentum has this property. But if we want to measure the momentum accurately, like this, that is, reduce the blur, the width of this, and make it smaller, then the position gets bigger. So we have these competing effects are what create the uncertainty principle. And it's not just position and momentum that apply. We saw the Stern-Gerlach experiment last week. That has its own pair of values that must be larger than Planck's constant over 4 pi. Energy and time have this same kind of relationship. For example, if you would like to measure the energy of an electron, you have to look at it for a while to refine your estimate of the energy. So it takes an interval of time, and no matter how long you look, you'll always have some uncertainty in the energy level, and that product has to conform with the uncertainty principle. Here's momentum and position. There are all sorts of versions of this. This is Heisenberg's microscope. depicted and with some description. And Microsoft Word has decided to do some updating again. But we have been together for an hour, so let's take about a 5 minute break, and then we'll resume and go on to some more details. So 5 minutes, and it's now 2 o'clock exactly. So I'll start talking again at 2:05. Okay, thank you. Okay, I'm back. Let's take a quick look at questions and comments. Hopefully, everybody's happy with the size of what's on the screen. Uh, if we're still having problems with that, post something. But I don't see any more complaints about that.
Would you like some questions or do you want to keep going?
While I'm looking at the chat, do you have questions other than the chat?
I do not.
Oh, okay. Yeah, I'll take a look at these and issue a question and answer sheet like I did last week. I hope everybody saw that I produced. Sorry, we get make this bigger. That I produced a question and answer sheet for last week's lecture. So now I have switched away from using Microsoft Word because it kept doing some kind of something in the background that was slowing me down. So we're now in a different environment. Is this clear enough, do you think?
It looks good to me.
Okay. All right. So we've talked a lot about theory. We have all these examples here of uncertainty principle that you can look at your leisure. But it's science is doing its best. Well, let's see. But somebody said there's no change in resolution. I made it bigger. Uh, I can't make it much bigger than that. Okay. Anyway, uh, science is doing its best when it can predict how nature is going to behave. And if we go back to the 1920s, Einstein had been studying what is called the statistics of particles in quantum mechanics. And out of nowhere, he heard from this guy, Bose, not the Bose who makes headphones, but a unknown scientist in India wrote to Einstein. It turned out he was working on the same thing, and the result of their collaborative effort was a statistical analysis of groups of atoms. And from this came the prediction that a group of atoms or quantum particles would have, under normal conditions, individual wave functions. But if enough energy was removed from their system, that is, if we made that system as cold as possible, they would coalesce into a single entity that could be described by a single wave function. And here we see a depiction of this, a group of atoms chilled, gradually getting more and more like a single quantum entity. And you see the University of Colorado, Eric Cornell, Wyman, and MIT's Ketterle produced what is called Bose-Einstein condensation. This is predicted back in the 1920s. It's hard to imagine that Einstein and Bose and their collaborators could have imagined this would ever be demonstrated. I mean, Einstein knew about the equations that we now interpret as describing black holes, but he could not have predicted that we would understand those things as well as we do. But here's Bose-Einstein condensation predicted by the use of the Schrodinger equation and cooling that group of atoms to 130 billionths of a Kelvin. above absolute zero. And it's an intriguing story, and the people involved, Carl Wyman is now focused on improving science education. I don't know if he's still active with doing this kind of research, but Eric Cornell is still at CU as a professor. So this is an extraordinary application of quantum mechanics to predict something and then actually go find it. Here's another one that's really intriguing. Dutch scientist Casimir in the late 1940s, using an extension of quantum mechanics, came up with an interesting scheme related to what are called vacuum fluctuations. That is, the uh, behavior of quantum systems progresses under the influence of the uncertainty principle. And the uncertainty principle allows, as I depicted earlier, I'll show it to you, it allows this energy and time to create virtual particles, particles that jump into existence with a certain amount of energy, so long as the duration of their life is small enough so that this rule is maintained, that the energy uncertainty and the interval of time is greater than this fraction of the Planck's constant. And Casimir realized this means that a vacuum that you might create in a laboratory could be filled with virtual particles all swirling around, photons, particles of all kinds. And the intriguing thing he came up with is if I take two metal plates and put them close together and treat these particles as having wave-like uh, reality, the ones with long wavelength properties, like this one, won't fit in there. So we embed these plates in a vacuum, and the whole vacuum is filled with particles of different wavelengths, but only the short wavelength ones will fit in here, which means there's less energy between the plates than there is here. It's kind of like the experience you have if you go up into the mountains and you have a bottle of Coke and you drink the Coke and you put the lid back on. I've done this for my grandkids many times. On your way down the mountain, you'll hear popping and creaking as the higher pressure in Denver collapses the bottle. The bottle was fine up in, Breckenridge or Aspen, but as you approach the lower altitudes and the pressure is higher, the bottle collapses. And this is what Casimir was talking about in the late 1940s. And it took 50 years to do the experiments to prove that these virtual particles would create a force between these two plates. I mean, the force is absolutely tiny, just very tiny. Here's a depiction of how the experiment might have been done. And you can see this curve, this smooth curve, is the prediction of Casimir's equations, and the dots are the measurements. So again, we see an example of the application of quantum mechanics to the real world and predicting a result, and then in this case, waiting 50 years for the technology to be mature enough to actually do the experiment, and sure enough, the theory and the experiment match. Another of extraordinary result of applying quantum mechanics is to calculate the magnetic properties of the electron. And this was done in the late 40s and early 50s and led to a Nobel Prize for Richard Feynman, the American, Julian Schwinger, American, and Tomonaga, Japanese. They each did a different version of the theory. They did not work together. They were independent researchers. They took completely different strategies for how to do the calculation of the magnetic properties of the electron. And the result, they both got, all three got the same result. See it here with this as an error bar. And by, I think, 1953, the measurement was made. And if you match the digits here, You have to get over to this digit before there's a difference between the theory and the measurement. This is the most accurate prediction in the in the history of science. And this has been improved some since the early 50s. Now, I've mentioned probably the first hour we were together that there's a quantum process, a quantum property of entanglement. And for me, it's the most mysterious of all the quantum phenomena. It says that quantum particles created together under the right circumstances are bound together in a mysterious way. They have, if one of them undergoes an experiment, the other will correlate with the results of the first experiment. So we always use Alice and Bob when we talk about these things. So if Alice makes a measurement on an entangled particle, her friend Bob, and no matter where Bob is, no matter how far away, Bob's result from doing the same measurement will be correlated with Alice's measurement. They won't know this till they get together and compare their measurements. And this lady, always known as Madame Wu at Columbia University, she was probably the first to create, in a laboratory, create a circumstance where entangled particles were created. She was a nuclear physicist, and she and her student were working with various kinds of experiments of this type, and they probably did not realize that they had observed entanglement. I mean, the process they used relates to radioactivity. So that goes on in the natural world. And she didn't invent entanglement, but she actually made measurements of entangled particles without realizing it. And there's some debate about this, but it seems likely that they did not realize what they were dealing with. So here's a cartoon. It's part of an article you can read. It's for the public. That is, it doesn't have any equations. And it's built around this piece of artwork related to pairs of entangled particles. Of course, there's Alice, there's Bob. And it's the same story I just told. Alice is over here doing experiments on entangled particles, and Bob's over here, and they're on the other side of, looks like maybe the United States. And they discover correlation when they get together. We will talk about this many, many more times in future lectures, but this property of entanglement is predicted by quantum mechanics. Schrodinger predicted it in 1935, and it took at least until Madame Wu did her work in the early 50s, and now it's a standard thing done in undergraduate laboratories. We're in the physics building at the local university. Now, another prediction. So let me just emphasize, we're talking about applications of quantum mechanics to predict things related to the natural world. Another prediction, an area of immense interest for the variety of medical materials and pharmaceuticals we have today, comes from understanding how you build the periodic table. Because if you can do that, you're on your way to understanding how to build molecules. But here, back in the early 1920s, the invention of quantum mechanics excited people because it, for the first time, gave them a tool for building a modern version of the periodic table of elements. Here's the version from the 1870s, which was based on how different elements known at the time interacted in chemical experiments. But to really build the periodic table, once the modern version of quantum mechanics was found, people realized we can explain how the periodic table works. That is, how the different electron structures influence the properties of the elements And in fact, the technique I'm going to show you predicted elements that were missing from this version. If you look closely here, here's copper and zinc, 63 and 65 on the periodic table. There's no 64 there. I'm not a chemist, so I don't know why. There was apparently no mechanism for doing a chemical experiment that would reveal that there is an element that fits in there. But gradually, quantum mechanics was put to the task of building this modern version of the periodic table. And in fact, this one pertains to where the elements come from in the cosmos. So here you have hydrogen and helium. All of hydrogen came from the Big Bang. Almost all the helium, if you look closely there, there's a couple little colors right there. They pertain to massive star explosions and low mass stars. And if you look through this, you see neutron stars are the purple areas. They are, if you want to find palladium, go find a neutron star merger, and that's where half of the palladium in the universe came from. So how does this work? We're going to skip this. The most important feature of the ability to construct the periodic table comes from the Pauli exclusion principle. Remember, we've talked about the three quantum numbers that pertain if you're describing a hydrogen atom or one like a hydrogen atom. Let's say you could take lithium and strip away a couple of the electrons, and so it's ionized enough that it has only one electron. Pauli realized that, and he did this by looking at the mathematics, that this quantum number, once again, it has to be an integer. This quantum number has to comply with a rule now called the exclusion principle, that the spin orientations of electrons in the shells of atoms can't just take on any old value. They have to fill up the shell without duplicating this quantum number. So let's stroll down here and I'll show you how this works. The exclusion principle says that no two electrons can have the same values for all their quantum numbers. This is the spin quantum number right there. So let me just describe this using a personal anecdote. So a long time ago when I was young, I had some friends who were dentists, and they wanted to be rock and roll impresarios, and they put on concerts, and I would go to the concert for free by working, unloading the truck and doing, that sort of thing. And I was also the announcer. And a lot of times for the lesser known acts, the community that wanted to see the concert would buy the cheaper tickets, and the front row tickets that were much more expensive only had a few occupants. And a lot of times the band would say to me, go out and tell the crowd if they want to behave, they can come down and fill these empty seats. One person to a seat. We don't want a mob scene in front of the stage. And so this is kind of what the Pauli exclusion principle deals with. If you have unoccupied energy, electrons in lower energy levels in the atom, electrons will come down and fill those seats, but they have to be respectful. No two electrons can have the same quantum numbers. Remember, quantum applies to energy level, orbital angular momentum, spin orientation, and so forth. And so we went from this situation to this situation where those empty seats got filled. The electrons behave this way. They're disciplined. They will not try to do this. They won't all try to jam up against the stage. And so that kind of thinking is what Ali had in mind. Of course, he wasn't thinking about rock and roll concerts, but he had looked at the mathematics. And there's a technical reason why this is true, that the electrons will fill the shells without duplicating any quantum number. So here we go. We're going to build the periodic table. And we use the German word Aufbau, which is the word for assembly. So here's hydrogen, and its ground state, it has one electron. In its ground state, that one electron is in some kind of a spin orientation. And that this symbol is not a number one, it's an arrow pointing upward. So at hydrogen, it's simple. One electron in the ground state, and it can be an up or a down, but there's no room for another electron because another electron would, there's only room for one electron in the ground state. So what happens if we add to the nucleus? So we have now two protons. Now we can add, or let me clarify something. The reason there's only one electron there is there's only one charged particle in the nucleus, the proton. And the atom itself is electrically neutral. It has 1 unit of positive charge from the proton and 1 unit of negative charge from the electron. So it's a stable system. If we add another proton, that changes the charge of the nucleus, and now we can get a stable element. We call it helium, and there's room for another electron, but it has to have the opposite spin. So we see here a down arrow. So we have an up and down. This is the ground state of helium. Now, what happens if we go to lithium? Now there's 3 protons, so we can introduce or invite another electron to join, but there's only room for 2 here. If this electron tried to get into this shell, they'd have a duplication of quantum numbers, not allowed. So we get a new shell is created to accommodate this new 3rd electron. And again, we have an electrically neutral atom, 3 nuclear charges, 3 electronic charges. Here's beryllium. Now we have 4 protons, and there's room for another electron. And this keeps growing like this. We don't have to go through the gory detail. Here's boron. Notice, as we build this, there's never a case where the spins are the same in the same energy level. And then chemists have this terminology. So they have hydrogen, that's the ground state. There's helium, that little 1 right there turns into a 2. Lithium is helium plus more electrons. Beryllium is helium plus even more, and so forth. So this is the modern version of the periodic table elements, and everything is accounted for. Remember, we talked about copper. Where's copper? I don't see it right now, but oh, here it is. We were missing something in here before. It had never been found in a chemistry sense, but quantum mechanics gives you this construction. So now we can appreciate the electron orbital shapes. That is, as you make more complex, larger atoms, you have more structure in the electron shells around the nucleus as you add more electrons. These are called orbitals. And here, color-coded, we see the distance from the nucleus of the electrons in different energy levels. Here's argon. So it has an electron here very close to the nucleus. By the way, look at the dimensions here. This is 100 picometers. That's a trillionth of a meter. So everything's close together. So you have the argon has this electron, and then the second shell, indicated by the 2, the probability of finding the electron there is here. Here's neon, helium, and so forth. And some of the numbers here are available to you. And here's the relative size of these atoms, the atomic radii. So this is the periodic table again. You see there, let me see, I want to make this bigger. There's a limit to how big I can make it before it just gets too fuzzy. Let's see, I can, yeah, that's as big as I can make it. It's quite readable in the book. But there's the size of hydrogen. Helium is smaller. Remember, I pointed this out before the break. Helium has two protons. So its electric attraction to the electrons is stronger. And in fact, the whole atom is smaller because of that. But when you get these more complex, larger atoms, they're physically much bigger than helium or hydrogen and so forth. Now, let's look at, we haven't really delved into the properties of the Schrodinger equation in 3 dimensions yet. So I want to show you this. Here's a reminder. This is what the Schrodinger equation looks like. It only depends on this. This is the one that is not changing with time. And there's Planck's constant. And I never mentioned it, but that little slash means you take Planck's constant and divide it by 2 pi. It's a shortcut. But here's Planck's constant and the mass of the quantum particle. But this is a one-dimensional property. Changes, it only depends on one dimension. How do we do 3 dimensions? When you have 3 dimensions, imagine Earth has 3 dimensions. It has a radius. So here's the Schrodinger equation. And you'll see little r's all over the place, here, there, and everywhere. That's the radius. And then we have the latitude and longitude of Earth. This is the latitude, and that is the Greek letter for the longitude. So it's this equation, and if you go through it, just ignore all these little symbols that have to do with math. And we have this, that's the charge of the electron. And the only thing left that I haven't described is this little letter there, that's the equivalent to the mass. And this little thing here with the 0, that's a property of empty space. So it's a little more complicated, but just don't let it bother you. To me, it's like a piece of artwork. All this graceful ink produces the wave function that we see here, and it has 3 dimensions. So again, we're looking at energy levels, and there is the 2-dimensional depiction of where the electron is. Here it is in 3 dimensions. And in this drawing, you can see even more carefully. The electron is never in this white area. It's called a node. It's this empty space here. There's just no place for the electron there. And again, the energy levels go as integers. This is n is always an integer. And we do have pictures of this. You can click on this and see details. There's a experiment, I've sketched it out here, where they actually have a sample of an atom and they tease it with a laser and spread out the energy levels using something called the Stark effect. And on the screen over here, you can see the locations, the probability distribution for the electrons in the outer shell. Now, I've already said this, the theory of quantum mechanics that we use today existed in the late 1920s and hasn't changed very much. But extensions have been made, and a key extension is called quantum electrodynamics. This describes how charged particles interact with light. And here's one of the pioneers of this, Paul Dirac, a Nobel Prize winner. Starting in the late 1920s, he and a few others developed this theory And it's what produced those extraordinary predictions of the magnetic properties of electrons that I showed earlier. And they did it by understanding the virtual particles interacting and colliding with each other. Remember the Casimir effect, which has now been confirmed in experiments, requires the theory requires the existence of virtual particles coming into and leaving the quantum world because of the uncertainty principle. So there's this constant swarm of, of particles that arrive and disappear, and they influence the behavior of charged particles. And Dirac figured this out. Here's one way to depict what happens. Here's an electron sitting, if you put it in a vacuum, sitting there by itself, but immediately the vacuum fills with virtual particles, these little things that are the elliptical shapes. And the virtual particles have charge. And they notice this negatively charged electron. So the positive charge of the virtual particles tries to get close to the negative charge of the electron. And in the process, from the outside world, the charge of this object gets shielded. So we have a charged particle in a crowd. It's like a celebrity drawing a crowd. It's hard to see the celebrity because he's surrounded by these virtual particles. And figuring out how to compute this influence was difficult, but Dirac started the problem. And then Schwinger, Feynman, and Tamanaga, I already mentioned, they, by the early 50s, had worked out the results. And the intriguing thing is that if you look at the energy levels predicted by Bohr's version of, say, hydrogen, he sees a single level for a particular electron shell. Dirac's result shows that no, if you look really close, there's actually two energy levels there. They're very close together, but they are there, and they are induced by this influence of the virtual particles. And then the modern version of quantum electrodynamics sees that even this level, if you look close enough, you'll see two levels. And in fact, experiments go on all the time to explore this. So once again, here are the results of the work in the late 40s and early 50s, which were extraordinary, but the work goes on. And so there's some history here that you can read. Here's Feynman, Schwinger, Tamanaga. The interesting thing is, I've already mentioned, they all three use different methods for computing magnetic properties of the electron. And when they got together, they could not explain to one another what they had done. There's one person who knew all three techniques, and that was this guy. Freeman Dyson did not win the Nobel Prize, but there was a time when he knew more about what these people did than they did, because he was able to show that their techniques, while completely different, their techniques were equivalent. And there's a little story here about the time I met Freeman Dyson. So, quantum field theory is the extension of quantum mechanics that now is the focus of how computations are done. The Schrodinger equation produces results. A more elegant way to deal with the quantum world is this quantum field theory that's existed since the late 1930s. And there's some details here as and here's a picture of what is called quantum foam. This is a depiction, an animation of the dynamics of the quantum world. Let me make this big for you. So this is a cartoon version of the appearance and disappearance of virtual particles interacting with each other and then fading away immediately. The lifetime of these particles is extremely short, measured in billionths of a second or less. And you see here's the famous Steven Weinberg, also a Nobel Prize winner, saying, the basic ingredients of nature are fields. This is the modern way of dealing with quantum mechanics. And the particles that appear are derivative from the fields. So we're not going to get too much into this except to say that there is information in this table and other places in the book about the properties of quantum field theory, QFT, and some limitations that it exhibits. Now, there's a cartoon for your. Now, here's one of the great applications of quantum mechanics. As you've heard from me in all of these lectures, quantum mechanics was invented to explain the behavior of atoms. How are the atoms behaving with respect to the electrons behaving with respect to the nucleus of the atoms? And the surprise was that quantum mechanics also works for the nuclear part of the atom. We should not have expected this to be the case. I'll just point out that the distance, the size of the nucleus compared to the size of the atom, there's a huge scale difference. The atom is much, much bigger, billions of times bigger than the tiny, tiny little nucleus at the center. And yet, quantum mechanics, invented to describe the behavior of atoms, works in nuclear physics as well. Now, extensions had to be made, but the fact that you can apply quantum mechanics to the far different nucleus is an extraordinary gift. And a great deal of it was done in the 1930s. Here's Enrico Fermi, who's very prominent in making these developments. The really extraordinary time is 1932, because you see neutrons and positrons, I'm supposed to say and positrons were found. Let's fix that. And Heisenberg got involved in nuclear physics. He had already had the success of developing a version of quantum mechanics as well as the uncertainty principle. But once he looked into the nucleus, he produced some insights that led to the proposal that neutrons and protons, which were already known, are in the nucleus. Yeah, the history of this is that the nucleus was not understood, except that it was realized that the nucleus was the source of radioactive particles flying out of certain kinds of atoms like radium and uranium. Radioactive atoms were producing pieces of energy coming out, particles and photons. So this is a history just in the 1930s, a tremendous development in the 1930s. And of course, the big issue was once people realized there was such a thing as a chain reaction, now we're on the verge of developing a nuclear weapon. And that was a startling thing for a long period of time. All the work on nuclear fission, natural nuclear fission and artificial nuclear fission, was in the public domain. People were publishing science articles. It wasn't until right before World War II that the physics community started communicating with the political community about the possibility of nuclear weapons. And of course, that changed everything about how nations deal with each other. So we have some history here, a discussion of particularly 1932 and all the developments that occurred that revealed the mechanisms, descriptions of mechanisms for the decomposition of the nucleus, the gradual conversion of the nucleus. I showed you an animation earlier in this lecture of how the radioactive release of a particle or photons can change the structure of the nucleus of an atom. It was also discovered that, and this is in the 1960s, that the neutron and the proton, the subatomic particles, are not indivisible. In fact, in that period of the 60s, the invention was brought forward of the concept of quarks. These are components of the neutron, and they have exotic names. The up and the down quarks, if you have two downs and an up, that's a neutron. And the neutron is unstable. If an isolated neutron lasts about 10 minutes and then the half-life has a half-life of 10 minutes, and one of these down quarks turns to an up quark, and that's called a proton. And it turns out the proton, as far as we know, protons are stable longer than the life of the universe. But all these dynamics of the subatomic particles and how they interact in the nucleus of particularly heavier elements like uranium, plutonium, and so forth, that really became understood starting in the 1930s. What's more, Hans Bethe in the late 1930s, 38 or 39, produced the first real working theory of how the sun produces energy. The physics, the quantum mechanics of that day was sophisticated enough that he was able to explain the creation of energy deep in the sun. And of course, today we have all sorts of applications of nuclear physics, many of them in medical situations, but also nuclear power, nuclear weapons, imaging for medical research, geology, and so forth. And what has evolved from applying quantum mechanics to the nucleus is a standard model of particle physics. It's the most successful model for the structure of the subatomic particles. And it explains the existence of and the properties of the components of the subatomic world. The physics, the laboratories where work is done include the big facility at CERN. This is French for the European Center for Nuclear Research. And this is a depiction of the various accelerator rings that exist at the CERN facility here in Geneva, underground, and the path around this biggest ring, the Large Hadron Collider ring, is 27 kilometers. I've had the opportunity to go down there and be in the underground laboratories of the facility. They have independent labs on different sides. For example, when they went looking for the Higgs boson, which was a big thing in the physics news in 2012, they had two groups looking for it. They're not allowed to talk to each other. This group found evidence, and so did this group. And so once they compare their results, you have confirmation, at least high credence, that you have found something. Another thing they produce at CERN is when the big accelerator is running, they produce a beam of neutrinos. These are ghostly particles that the sun produces in huge quantities. And though that neutrino beam goes through Earth like it's not even there and encounters a research facility in Italy where they study cosmic rays and neutrinos. But the big success of applying quantum mechanics and its derivatives to the subatomic world is this table of the standard model of particle physics. Here's a bigger version of it. I hope this is, oh yeah, here's a bigger version. Here are the quarks I mentioned. And every one of these particles, except this one, has an antiparticle. So we have the up-down charge strange top and bottom quarks, and they are the constituents of neutrons, protons, and other subatomic particles. Then you have this group of really the electron family. The electron, a heavier cousin, the muon, and a much heavier cousin, the tau, and each one of them has associated with it a neutrino. So there's different kinds of neutrinos. And again, all these guys have antiparticles. The antiparticle of the electron is called the positron. And this model, including the predicted masses and charges and behavior, is the standard model of particle physics. And as I say, it's extremely successful. Here's another depiction of the electron family. So we have the electron, which has a certain mass and charge, the muon and the tau. And then these quarks, the up and down, are associated with this family, sort of in green. The charm and strange quarks, the muon and the muon's neutrino, they're in another group. And then you have this group for the tau and its quarks. And the size of these spheres represents the mass of the various subatomic particles. And standing alone here and here is the Higgs boson. As a complicated history, but it was found in 2012 after it was predicted by Higgs. So there's some information here about decomposition. This is a summary of everything we know about the standard model. And there is work underway at CERN and other places to see if there is a extension to this family of the standard model called supersymmetric particles. Every once in a while, let's say every 5 years, somebody comes forward and says, we found supersymmetric particles. They are predicted by the theory, the quantum field theory predicts them, and there's no tangible evidence of supersymmetric particles yet. So, as we finish up here, and by the way, I am watching the chat box. I don't see any other questions popping up. What are the applications of quantum mechanics outside of chemistry, nuclear physics, and so forth? And an extraordinary application has been to explain the behavior of astrophysical objects, namely white dwarfs and neutron stars. And this has been extremely successful. As you see here, back in the 1930s, Chandrasekhar predicted the behavior of white dwarf degenerates. They're called degenerate stars. If you have a white dwarf, which is just made up of electrons, in the vicinity of another much bigger star, if matter flows from the big star to the white dwarf, eventually the white dwarf gets to a point where it cannot sustain its existence, and it collapses in a supernova event. And Chandrasekhar was able to calculate, using quantum mechanics, how massive a white dwarf can exist before it explodes. And it turns out to be just a bit larger than the mass of the sun. And we now regularly detect supernova events, and we understand the dynamics that goes on. And this has had Uh, Intellectual achievement is great, but it also has an application in understanding the expansion of the universe. And if you take my class on cosmology, which I'm going to offer at CSU next year in the January semester, I'll explain what I'm talking about. So, a lot of success in understanding neutron stars, white dwarfs. I already mentioned Hans Bethe successfully showing how the sun produces energy. And in the process, the questions came up about all the neutrinos that are produced by the production of energy deep in the sun. And it took 50 years of research to understand that process, what's going on with the neutrinos created in the sun. Right now, for each of us, billions of neutrinos are passing through every square centimeter of our body every second. And these are coming from solar neutrinos. And so these three Nobel Prizes were awarded for experiment and theory to explain how the sun produces energy and neutrinos associated with that process. And you can just scan over this. This is kind of a description of how that process works. So once again, here's the periodic table now understood in the context of how the elements in the universe were produced. And this data is compared with what is measured in galaxies. If you do astrophysics and look at galaxies, you can find helium, lithium, beryllium, and so forth, and compare the amount of those elements that we see in the universe with the production rate that is predicted by quantum mechanics. And the agreement's pretty good. We also have lasers. They were predicted by Einstein early in the days of quantum mechanics, and we have lots of other light emitting diodes, superconductors. We have two prominent ways that you can observe quantum effects with your naked eye, and that is superfluid helium. If it's made cold enough, helium flows without resistance, and superconductivity provides techniques for making very large magnetic fields. So if you've ever had an MRI, you've probably been in the vicinity of superconducting magnets. And so our takeaways are we have a theory that works. It's been working for the last 100 years. It works for atomic physics. It works for nuclear physics. And the modern version of quantum field theory has been very successful in describing the subatomic world and the subnuclear world, that is, the quarks and all the related particles that make up protons, neutrons, and other subatomic particles. We also now understand tunneling. The uncertainty principle is a standard part of quantum mechanics. None of the fundamentals that were understood in 1927 have been proven wrong. All of that theory has been put to work and is successful. Extensions have been made, but nothing was defective about the version of quantum mechanics that existed in 1929. So with that, unless there are questions, we're going to end for today. And next week, what we'll talk about is the concern that comes up in how to interpret all this success and trying to understand how the quantum world works. Why does it work the way it does? We know it works. The question is, why does it work the way it does? So with that, I'm going to let our monitor end the session, and I look forward to seeing you next week.